experiment before. So did the procedure look pretty straightforward, or what? Were there any questions about the procedure, like anything specific about the procedure you want me to address? One of the things about this is we're going to use the LabQuest system for this, and so for the spectrometer, it's a little bit different, and then it's similar also. And what we're doing today is something called spectroscopy. There are many different kinds of spectroscopy. Today we're going to do UV vis spectroscopy. UV vis spectroscopy just stands for ultraviolet visible. And what spectroscopy, all these many different kinds of spectroscopy do, they all do the same thing. They all measure the interaction of light and matter. And so it's quantitative measurement of the interaction between light and matter. And so, for example, infrared spectroscopy measures the interaction of infrared light and matter. UV vis spectroscopy, what happens in the ultraviolet visible range? We'll just call it UV vis. What happens to matter when you shine visible light on it? When visible light shine on matter, what happens? Brandon, you on? All right. Oh, go ahead, Lily. You're not disturbing the mass. Exciting the electrons. Good. You're exciting the electrons in matter. That's what I was looking for. And so we're going to excite the electrons in matter. Well, when we excite the electrons in matter in the visible range, it causes colors to happen. And we can see when we do this, we measure what's called a spectrum. The quantitative measurement or interaction leads to a spectrum. And so we have two types of spectra. Spectrum is singular, and spectra is plural. Turn this off. What we look at Tuesday was what's called the emission spectrum. So we have emission versus absorption. And so for emission spectra, what we look at here is let's go energy going across Roy G. Biv, and then ultraviolet. We look at the intensity of the emitted light. And so, for example, a light bulb, you want to see a good rainbow colors emitted. And so we call this a band of light being emitted. Do you want to see much UV light being emitted from your light bulb? No, what we hope to see is we hope to see very little ultraviolet light being emitted. And so what we'd like to see in a light bulb, especially if you're using it, is we'd like to see all the colors in the rainbow. We don't want to see much UV, if any. And we don't want a whole lot of infrared, because infrared is just giving off heat. It's not giving us light. Right? And so ideally, if you have a light bulb, what we'd like to see is we'd like to see a broad band of emitted radiation. We call this emitted, and it's just the white light being emitted. As far as absorption goes, it's a little different. In absorption, what you do is you shine all the colors of the rainbow. So we shine white light at this and see how much of that white light is absorbed. And then it might be, all the colors of the rainbow being absorbed. This would be an absorption band. So these are bands here. And so what happens is, if all the colors are being emitted like this, we get white light. That's what we call white light. However, on the other hand, if all the colors are being absorbed like this, what happens when all colors are absorbed? You know what color it appears? It appears black. So this would be a black object. Colors arise when, no light is absorbed. If no light is absorbed, what does it look like? If no visible light is absorbed, let's go Roy G. Biv. And we're looking at, what color does it appear? It's either going to be white or transparent. And so we'll just say transparent or colorless. No colors absorbed. Actually, we're going to focus on absorption because that's what we're doing today. We'll talk more about emission later. And so this is what we're doing. Let's say if only one or a few colors is absorbed. And so out of all the colors, what we're doing is we're shining all the colors of the rainbow on this object and seeing which colors are absorbed. And if green is absorbed, let's say green is absorbed. And so what we'll see is what we call an absorption peak here. The peak. Absorption peak. Or, it could be an absorption line. A line is just a narrow, very, very narrow peak. But let's say green is absorbed. What color would the object look like? Would the color look green? It turns out if you take out all the green out of a rainbow, then the remaining colors add up to what? If you remove the green out of a rainbow, then the remaining colors don't add up to white. White light we only get if we have all the colors of the rainbow. However, if we don't have green, then what does the light appear in color? And it turns out it's not green. It doesn't appear green. If you remove the green, let's say all the green light's being absorbed by this object, then what we use something called the color wheel, the artist's color wheel, in which we go red, orange, yellow, green, blue, and then purple or indigo violet. Indigo violet we'll cram into one, call that purple, something like that. And so this is the color wheel. And so if some object absorbs green, then all the other colors add up to what we call its complementary color. All the other colors, take a look, will average out to red. And so if something absorbs green, it has a red color. Let's see. Well, plants look green. Since plants look green, you know, the leaves are green. What color light are the leaves absorbing, you say? Well, you know, simply we would say that, you know, the plant's leaves look green because it's absorbing red light. Although plants, the chlorophyll in plants is a little bit more complicated because we can absorb more than one color. If we absorb more than one color, then we got to look at how the remaining colors average out. So let's say we absorb all colors. I'm going to absorb all colors. So if I absorb orange, yellow, I forgot what it's B. If I absorb red, orange, indigo, violet, I'm only going to be left with, let's leave orange. Let's leave red. If I absorb all colors except for red, green, blue, do you know what red, green, blue add up to? White light. And so we could form different colors or even white light by mixing these. And so artists are very aware of mixing colors. And the same thing happens here. And so does it make sense? Plants are going to absorb a lot of red because from the sun, you know, the red is pretty intense. The infrared and the red are pretty intense. And the indigo violet and the ultraviolet drop down in intensity, at least on Earth. All right, so we're going to measure the spectra of different objects. Actually, we're just going to do different concentrations. Let's take a look at let's take a little look at an animation. Spectroscopy here. These are just colors of the light rainbow. Whoops. This is how we excite the electrons to different energies here. I'll talk more about this next time. So the electron absorbs some light and gets excited. So it goes from a lower energy to a higher energy. All right, that's it. That wasn't that. Looking for. But let me show you what we're doing. Okay. And so how do you take an absorption spectrum? You pretty much have a light bulb. We're going to use LEDs, but you could use a white light. And so there's going to be a light source. This. And this light source is going to emit white light. Now, does water have color to it? Does water have color? No. The water is invisible to white light, right? To visible light. But is it really invisible? Can you see water? Or is it really invisible? You can see it, right? You know if your cup is full of water or if it's empty. So it's got to interact with some visible light, correct? And the same thing, if you have a test tube, a test tube is colorless. Well, actually, you might notice that some glasses do impinge a color to it. But, you know, for the most part, a test tube's colorless. But is it really invisible to visible light? No, it's just not absorbing. But what's happening are some of the light's being scattered so we could see it. We could see the test tube. We could see water, right? Even though it doesn't have a color. If something doesn't have a color, what's happening is this. You know, it's not absorbing any of these colors of the rainbow. It's just transparent. It's colorless. But it still scatters light. And so what we do is, you know, it depends on the age of the light bulb and other things. Do all light bulbs give off the same intensity of light? Like if you went to the store and bought two 60-watt light bulbs, do they have exactly the same intensity to, let's say, 6 sig figs? No, because of manufacturing, etc., variations. Not all light bulbs give the same intensity of light. And then the same thing, do you think all test tubes are made to the exact same standards? Each of them are precise to the nearest nanometer? You think so? Like all Erlenmeyers are exact twins? Like if you mixed yours with your partners, you couldn't even tell the difference because they're exactly the same to the atom? No. The things are a little bit different. And so the amount of light that's going to scatter from the water depends on the water sample and the test tube. We have special test tubes for this. The test tubes that we use are called cuvettes. And the cuvettes are as optically pure as possible. They try to make this so it doesn't absorb any of the colors. Because if it did, then, you know, it'd be a little error associated with that we'd have to correct for. And so typically we use a very special glass for test tubes that we use in spectroscopy. These test tubes are called quartz cuvettes, and the quartz is very good because quartz, you know, a lot of things will start absorbing in the UV. We're just looking at the visible here. Our light bulb doesn't emit much UV, but you know, most substances will start absorbing UV because UV, what happens? UV energies. I'm sorry? Exciting electrons, yeah. Then UV, something else happens. It breaks bonds. Good. Breaks bonds. And so it turns out, well, the quartz bonds are very strong, so it's hard to break those bonds. So quartz is pretty transparent to some UV as well, whereas normal glass will start absorbing in the UV. And so if you want to measure some UV spectroscopy, then you need as transparent of a container as possible. And so what we're going to do is we're going to put this cuvette in the beam, but the cuvette's going to scatter some of the white light. And so what we have over here is we have a detector. Over here we have a detector. And the detector, well, if some of this light is scattered, what's going to happen? What's going to happen is that the full intensity of the light bulb is not hitting the detector, right? And so each item you place in front of here, the amount of light that's actually hitting the detector is going down, right? And so this is what we call a blank. A blank is everything except what we're trying to measure. Now, we're trying to measure red food color. And so red food color is water soluble. We'll put it in water. But what happens is we just want to measure the light interaction with red food color. We don't want to measure the light interaction with the cuvette. We don't want to measure the light interaction with the water. Just only the red food color. And so a blank is everything except the sample, the analyte. The analyte being red food color. And so what we do is, first thing we have to do is we have to blank or zero the spectrometer. And so when we do this, when we put this blank in here, then we have the maximum amount of white light hitting our detector. Right, the maximum amount of white light hitting the detector. And that we call a zero absorbance, basically. Is absorbing none of the colors of the rainbow. Now our detector is going to detect the spectrum. And so with our blank in there, it should just be a flat line. Now what I'm going to do is I'm going to tilt that on its side, looking at it vertically like this. Now if I put something in here, like this blue stuff, so now I have some blue Windex in here, right? And now I'll put this blue Windex into my sample compartment here. Now the Windex is blue, and the blue color can come from absorbing a single color, like what? If this looks blue, I must be absorbing, let's see, the color wheel here. I must be absorbing orange. And so one way I can make blue is I have an absorption peak at orange. Then I would get a blue color like this. But there are other ways. You know, just like red, green, blue add up to make white light, I could come up with other combinations to make blue. For example, if I absorb what mixes to make blue? Yellow and green? So if I have absorbed yellow and I absorb green, it's going to appear blue. Does that make sense? And so there are multiple ways. Well, how can I tell? Well, the easiest way to tell is not to guess. The easiest way to tell is just put the sample in here and then look at the spectrum. One possibility that we said is it's going to absorb orange. If it absorbs orange, we'll get an absorption peak at orange. All the other colors will add up to blue. Or you know, it might not have this. It might be an absorption peak at, what did we say, yellow and green? Something like this. Yellow and green, and then it's going to look perhaps blue, or maybe I have it backwards. But anyway, what we could do is we could just measure the spectrum. The spectrum is going to tell us what colors of the rainbow are absorbed. And so we're doing red food color. And so if we're doing red food color, then we must be absorbing green or another combination of colors, you know, to get red. So what we're going to do, I'm going to do the discussion in parts. So the first part of this lab is we're going to measure the spectrum of red food color to tell us how is that red food color red. All right, so I'm going to stop here. I want you guys to check out the equipment from the stockroom, and we'll measure the spectrum of red food color.